Okay, in this video, I want us to take a look at some molecular models that I've built and discuss the geometric shape, the angles, and so forth found in these molecules. Now, I am making an insight that you've already watched the Lewis dot structures video, and you've reviewed your class notes and textbooks on Lewis dot drawings and Lewis dot diagrams for compounds. Okay, so what I've got here is I've got a series of models that I want us to walk through and look at the shapes and look at the bond angles and so forth as a review. Okay, so this right here is an example of a compound such as carbon dioxide. Okay. Carbon dioxide's Lewis dot diagram would look something like this. Okay, with double bonds existing between the carbon and the oxygen atoms. Now, I've represented the double bonds with these purple pegs here, and then the lone pair of electrons that are found on the oxygens I've represented with the gray pegs. Okay? So as we look at this molecule, what we see is we see a linear pattern between the central atom and the surrounding bonded atoms. Okay? And on the bonded atoms here we have these two lone pairs of electrons, but the bond angle, so the angle between these, you can see is in a straight line. Okay, and it doesn't matter if I turn it this way or that way, it's a straight line. It's what we call a linear geometry, and that angle, that geometric angle, is 180 degrees. Okay, so that angle between there is 180 degrees. So this is what we call linear geometry. Okay, examples, you would see this in carbon dioxide, but you also see it in carbon monoxide, or you see it in hydrogen gas, it's found, nitrogen gas, so liquid nitrogen, if you're familiar with that. The bond angle between it is 180 degrees. It's got this linear style of geometry. Okay, so there's some examples of linear geometry. Okay, now I'm going to flip my paper over and let's take a look at this molecule. Okay, this model here. Now, we've got our central atom, okay, and on that central atom we have three bonded atoms, okay, and I'm representing these single bonds with the gray pegs. And if we just set it here and we kind of trace that shape, that geometric shape, looks like a triangle. Now, as I rotate the model, notice how the three bonded atoms are all in the same plane. They're flat. See how they're flat? This geometry is called trigonal or trigonal. I've heard some people call it trigonal. Think of triangle. Planar. Okay? And the bond angles, if we measure the angle between each one of these, okay, we would be seeing bond angles of 120 degrees, okay? 120 degrees between here and here. That angle right there is 120 degrees, each one of those, okay? Example of compounds that will have this, things like BF3 or BCl3 would be that, and aluminum chloride, if we drew a Lewis structure for something like that, aluminum chloride would also have a trigonal or trigonal planar arrangement. Okay, let's go to another model. Now, you've noticed we are increasing the number of bonded substituents around that central atom. Here we have 4. Now when I set this down, notice these are not all in the same plane, and as you rotate, they are not. Okay, example of this is natural gas, methane, is an example of it. Here's Lewis dot structure for it. Okay. This is what we call a tetrahedral. A tetrahedral arrangement. Okay, this is a tetrahedral geometry. Notice these three are much alike. See how it stands up, and then this one is coming straight up. If you rotate it, same thing. It's called a tetrahedral arrangement. Okay, I gave you methane, natural gases. Another example is carbon tetrachloride does this arrangement. It's a very common arrangement. These angles, if we measure these geometric angles, they're 109.5 degrees. Okay, 109.5 degrees. Okay, where the trigonal planars were 120. Notice as we add another substituent bonded here to fulfill that octet rule, the angles are getting smaller. We're going down to 109.5 degrees. On a side note, a water molecule that's H2O has this arrangement. It does have a tetrahedral style of arrangement, but it's called a bent tetrahedral bent geometry. These lone pairs of electrons that exist, if this is your oxygen, these two are your hydrogens, there's still two lone pairs of electrons on the oxygen, cause a reduction in the angles. These angles, now that these are open, that higher energy lone pairs of electron causes crowding and causes change in the angles. It drops it down to 104.5 degrees, so a little bit smaller. Okay? Alright. Let's move to our next model that has 5 substituents. Okay? Can you see all that around there? Okay, so I'm going to hold it straight like this. And you look straight down through here. Notice that this blue and the one there on the bottom are in a straight line. Okay, so see that straight line straight across there? Okay, those angles you can pretty much see are 90 degrees. The angle between this and this one, this and this, 90 degrees. But now when we look straight down upon it, okay, what do you see between these three? Right here, we see a triangle. We see a triangle. So in this arrangement, this is what we call trigonal, see the triangle, bipyramidal. Trigonal bipyramidal. Okay, trigonal bipyramidal, because if we look at this sideways, okay, this will give us a pyramid shape. Okay, and then we have another one upside down from it. So this is trigonal bipyramidal. There's 2 bond angles here. There's 90 degrees that we see when we look straight down the line, and we look between here and here, we see 90 degree bond angles. But when we look at the triangle portion, we see 120 degree bond angles. Okay, and some examples that do this, PCl5, what we call phosphorus pentachloride, is a great example of this. On this style of geometry, molecular geometry, we have an expanded octet. Okay, we're above the 8 electrons needed to fulfill the octet. We actually have 10 electrons crowding this central atom. With each bond being, a pair of electrons, we've got 5 pairs. We've got a total of 10 electrons involved in this arrangement. Okay, with a trigonal or a trigonal bipyramidal. Okay, all right. And then our final model is an expanded octet going above the octet rule of 8. We have what we call an octahedral arrangement. Okay. Now, octahedral, when you hear octa, you might often think 8. You might often think of 8, but with that prefix. But here we have 6. We have a total of 6 bonds around the central atom. Okay, so we have a total of 12 electrons. We have an extra expanded octet. We have 12. Now, and if we've noticed, here's a straight line forming. Okay, let's turn it. See, there's another straight line. Turn it this way, another straight line. There's lots of straight lines in here, lots of linear style of arrangements, it looks like all of the angles, you probably can tell, are 90 degrees in these bonded atoms. Okay, do you see that? 90 degrees. Okay, no matter which way you turn it, 90 degrees are the bonded angles. Okay, a prime example of this geometric arrangement is what we call sulfur hexafluoride. Okay, sulfur hexafluoride. And it's a pretty neat compound. You should take a moment and Google that, SF6, sulfur hexafluoride. It's a very unusual gas. It's got a very high density. It's a very, very thick gas, so to say. But if you look up some videos of it, you'll find some intriguing videos of sulfur hexafluoride. But this is an octahedral arrangement. So in each one of our models that I showed you, you notice that the bonded atoms and the lone pair of electrons arrange themselves in such a manner that they maximize the distance between the bonded atoms. Okay, this maximizing the distance, maximizing the angle between those bonds and those lone pair of electrons is the foundation of a theory that we often refer to as VSEPR. Okay, VSEPR theory. Okay, it stands for valence shell electron pair repulsion. Valence shell electron pair repulsion. Okay, and VSEPR theory is the idea that when molecules are built and the geometric arrangement is established, that the bonded atoms and the lone pairs of electrons will arrange themselves, will orient themselves to be as far apart as possible. Okay? Because even though the electrons are involved in bonds, they're still electrons and they're still going to be repelling each other. Okay? So these electrons in and out of the bonds are going to be repelling each other. So there's repulsion forces. So they're going to maximize that distance between themselves. And so we can predict those bond angles based upon these simple arrangement models and give us more insight of the three-dimensional shape, structure, and orientation of our molecules.